Okay, I apologize for the fact that I have a cold and that my boy is sleeping upstairs and I'm trying to be extra quiet, but here we go. The natural logarithm as an integral. Well, in Calculus 1, we defined e to the x to be the exponential function that had a slope of 1 as it crossed the y-axis. Now, we defined natural log of x to be the inverse of this one-to-one function. However, it wasn't a very useful definition to work with. For instance, how do we figure out what e is exactly? Well, a calculator will tell us it's 2.81 something something something, but this enabled us to find all the usual properties of e to the x and ln of x. Well, today's lesson, we're going to talk about how we could define the natural log of x to be the integral from 1 to x of 1 over t dt. That is, pretend you don't know what the natural log is. Pretend you don't know what e to the x is. This is our definition. This is our new way. And let's see, what can we say? Well, just as the fundamental theorem of calculus said that if big F of x was the derivative, the integral from 0 to x of f of x dx, then the derivative of big F of x was little f of x. The exact same reasoning will say that the derivative of the natural log of x, defined as such, is going to be, well, not 1 over t, but 1 over x. So, just straight from this, the derivative, you could do the whole thing, limit as h goes to 0, ln of x plus h minus ln of x over h, and you're going to see it's a little sliver that's h wide and is defined by the function 1 over x at the point t. However, actually, we even had to do that as well, didn't we? We had to have t's over here. And it did turn out to be little f of x. So we've got the derivative of natural log is just what we want it to be. What else can we say? Well, we know that the natural log of 1 is the integral from 1 to 1 of 1 over t dt, and that is an area under a curve of width 0. It goes from 1 to 1, and that would be 0. And so that gives us another property of the natural log that we like. The natural log of 1 is 0. This also enables us to say, well, what is the function? Well, that enables us to say that the graph of y equals ln of x, well, we know that it goes through 0. Over here we know that the curve y equals 1 over t looks like this. When t approaches 0, it goes off to infinity. As t gets big, it gets small. And so we're taking the area from 1 on, well, up to x, let's say. So, right. So, I'm not going to be able to shade that in very well. But this, as you can tell, this function, 1 over t, is always above the x-axis. So the area is always going to be positive. And as x gets bigger, we're going to add more and more area. If we use a number less than 1, then we've got the terms of integration reversed and it will be a negative number. This just goes to show that the graph of natural log of x looks, well, like it's supposed to. It's 0 at 1 because natural log of 1 is 0. It's just increasing. We add more and more area. But notice that its slope at x is 1 over x. That's what its derivative being 1 over x means, which means that as x becomes big, the slope becomes pretty shallow, pretty flat, flat-ish. There's probably 2 t's in flattish. In any case, the curve, it's always going up, but it goes up more and more and more slowly as you go along. This is the classic natural log of x function. What else can we say? That is it for now. I'm going to make a different video that talks about more properties of natural logs using this definition. Oh, one more thing. This function happens to be 1 to 1. You know, y equals ln of x is 1 to 1 because it satisfies the horizontal line test. Whoa. Every horizontal line hits it in exactly one point, and therefore it has an inverse. It has an inverse, which we will call, that's right, e to the x. So rather than define e to the x first and then natural log of x as its inverse, we're doing the exact reverse of this.